To us, Earth feels vast. It takes days to cross it. Oceans stretch beyond the horizon, and continents seem endless. But the moment you leave its surface, that illusion collapses. What once felt immense shrinks into a fragile speck, suspended in a universe filled with countless planets, unthinkable numbers of stars, and trillions of galaxies stretching beyond comprehension. This is a scale we don't just struggle to explore, we struggle to even imagine. And yet, within this vast cosmic structure, there exist individual objects that push scale even further. Stars so enormous they make our sun look insignificant. Deep within the southern constellation Scutum, astronomers believe they may have found one of the largest stars ever known. But that raises a deeper question. Just how big can a star actually become? And more unsettling, are there even larger giants still hiding in the dark? So let's begin the climb, rising step by step into the upper reaches of the cosmos, where the universe reveals its true giants. You might think our sun is enormous, and in many ways, it is. With a radius of about 700,000 kilometers, it dominates everything in our solar system. If the sun were scaled down to the size of a football, Earth would shrink to something barely visible, a tiny peppercorn just 2 millimeters wide. And even if you combine the mass of every planet orbiting it, the sun would still outweigh them all hundreds of times over. But in the wider universe, the sun is nothing extraordinary. Some of our closest stellar neighbors, like the Alpha Centauri system, are similar in size, while Sirius A is already twice as large, which raises the question, how big can a star actually become? To answer that, we have to step back and understand how stars live, evolve, and ultimately transform. And that journey begins with one of the most important maps in astrophysics, a diagram that quietly reveals the life story of nearly every star in the universe. In the early 1910 decade, two astronomers working independently, Ejnar Hertzsprung in Denmark and Henry Norris Russell in the United States, developed what we now call the Hertzsprung-Russell diagram. It plots a star's temperature against its brightness, revealing patterns that at first glance seem simple, but hold the key to everything. Running diagonally through this diagram is a dense band known as the main sequence. This is where most stars spend the vast majority of their life, not in chaos, not in collapse, but in a delicate, steady equilibrium. After the violent collapse of a molecular cloud that gives birth to a star, something remarkable happens. Deep in its core, hydrogen begins to fuse into helium, releasing enormous amounts of energy. That energy pushes outward, resisting the crushing force of gravity pulling inward. When these two forces balance perfectly, the star enters a state known as hydrostatic equilibrium. Most stars you see in the night sky exist in this quiet equilibrium, but that doesn't mean they are identical. Their differences begin with something fundamental: temperature. And from temperature comes color. And from color comes classification. Stars are grouped into spectral classes, ordered from the hottest to the coolest as O, B, A, F, G, K, and M. Our sun belongs to the G class, sitting comfortably in the middle, with a surface temperature of about 5,778 Kelvin. It emits the soft yellow-white light that has illuminated Earth for billions of years. And inside its core, this quiet process never stops. Every second, hundreds of millions of tons of hydrogen are fused into helium, releasing energy that not only sustains the star, but makes life on Earth possible at all. As you move up and down the main sequence, a pattern begins to emerge. Cooler stars tend to be dim, hotter stars burn brighter. That part feels intuitive. But beneath that pattern lies something deeper, something more fundamental. Mass. The brightest stars are almost always the most massive, and with mass comes pressure, and with pressure comes power. Take Betelgeuse, for example, the 26th brightest star in the night sky, marking the left shoulder of Orion. It's a B-type star, one of the hottest classes. with a surface temperature of around 22,000 Kelvin, nearly 4 times hotter than our Sun, and it carries over 8 times the Sun's mass. Deep inside its core, that extra mass changes everything. Gravity compresses hydrogen far more intensely, raising both temperature and pressure to extreme levels. Fusion reactions accelerate, releasing vast amounts of energy. So much energy that the star begins to push outward, swelling against the very force trying to contain it. Bellatrix becomes enormous. Its volume expands to around 200 times that of our Sun, a reminder that in the universe, size is not just about how much matter you have, but how violently that matter behaves under pressure. But this power comes at a cost. Massive stars live fast and die young. While our Sun will quietly burn for around 10 billion years, Bellatrix has already lived for roughly 25 million, and may only have about 7 million years remaining. This is why the largest stars are rare. They are unstable, short-lived, and constantly on the edge of collapse or destruction. The universe simply doesn't give them much time to exist. So, does that mean the biggest stars are simply the most massive ones? Not quite, because here, the universe introduces a limit, a boundary set by physics itself. It's believed that stars cannot grow much beyond 150 times the mass of the Sun. Beyond that point, something begins to break. Radiation pouring out from the core becomes so intense that it pushes matter away, overpowering gravity itself. The star starts to tear itself apart from the inside. And yet, the universe has found ways around this limit. When two massive stars collide and merge, they create something far beyond what a single star could ever become alone. A true giant, formed not through slow growth, but through violent union. This may explain one of the most extreme stars ever discovered, R136A1. A name that sounds technical, but represents something almost unimaginable. Located at the extreme upper corner of the Hertzsprung-Russell diagram, R136A1 pushes far beyond what we thought possible. Its mass is estimated at around 265 times that of the Sun, completely ignoring the supposed limit. Its radius stretches to about 40 times larger. It belongs to a rare and violent class known as Wolf-Rayet stars. In our entire galaxy, we have only identified a few hundred of them, and yet, even that may just be a fraction of what truly exists. These stars exist in a brief and violent stage of life. Just before their final collapse into supernova explosions, they are unstable, constantly shedding themselves into space. Powerful stellar winds tear away enormous amounts of plasma, ejecting material equivalent to 10 suns every million years, at speeds approaching 1,900 miles per second. And yet, despite losing so much mass, they shine with unimaginable intensity. R136A1 releases as much energy in just 4 seconds as our Sun does in an entire year. To human eyes, it appears about 164,000 times brighter. But that is only because most of its radiation lies beyond our vision, in the ultraviolet. In truth, it is far more extreme than we can ever directly perceive. In fact, we are incredibly fortunate to have observed it at all. Stars like this live fast and vanish quickly. R136A1 may exist for only around 3 million years, a fleeting moment on the cosmic timescale. But even this is not the largest star in the universe, not in terms of size, because here, something unexpected happens. The most massive stars are not the largest one. The true giants emerge not in strength, but in decline, not while a star is stable, but as it begins to die. Up to this point, we've been looking at main sequence stars, stable objects fusing hydrogen in their cores. But eventually, that fuel runs out, and when it does, the balance breaks. Without the outward pressure from fusion, gravity begins to win. The core collapses inward, compressing itself to extreme densities. And with that compression comes heat, enough to ignite a new stage of fusion. Helium begins to fuse, and the star enters a completely different phase of life. But the core is not the only place that changes. The heat spreads outward, reaching layers that were once cold and inactive. Regions that never experienced fusion before suddenly ignite. Hydrogen in the outer shells begins to burn. And this is where everything changes. The star begins to expand, dramatically. What was once compact now swells outward into something enormous. A red giant is born. Right now, the Sun has a radius of about 435,000 miles. But in this future phase, it will expand to a diameter of roughly 186 million miles, large enough to engulf Mercury, Venus, and possibly even Earth itself. In that distant future, the sky would not be blue. It would be filled with a burning red star, stretching across the horizon as the oceans boil and the atmosphere is stripped away. And yet, even this transformation is not unique. Stars between about 0.8 and 8 times the mass of the Sun will go through this phase. One example we see today is Mira A. Mira A is only slightly more massive than the Sun, and yet its radius has expanded to more than 300 times larger, but even that is not its final form. It pulses, over cycles ranging from 80 to 1,000 days. The star physically expands and contracts. When these cycles align, it swells even further, pushing its outer layers into space. But even red giants are not the largest stars in existence, because beyond them lies another class, larger, more extreme, and far more unstable. When a star exceeds about 8 times the mass of the Sun, it can evolve into something far greater, a red supergiant. These are true titans of the universe, vast, towering, and nearing the end of their existence. They will eventually die in violent supernova explosion. But just before that moment, they reach their greatest size. And one of the most famous examples is Betelgeuse. Betelgeuse stretches to an almost unimaginable scale. Its diameter reaches roughly 750 million miles, making it more than 700 times wider than our Sun. If placed at the center of our solar system, it would swallow Mercury, Venus, Earth, and Mars without hesitation, and even Jupiter would lie dangerously close to its edge. But these supergiants are not solid, well-defined objects. They are turbulent oceans of plasma, constantly shifting, pulsing, and shedding mass. In their final stages, they erupt and expand so violently that the very idea of a clear surface begins to break down. Where the star ends and where space begins becomes impossible to define. And yet, even something this vast is not the largest star we know, because hidden deeper in the galaxy, in the constellation Scutum, lies an even greater giant. Its name is UY Scuti, and calling it large is an understatement. It is so vast that billions of suns could fit inside its volume, a scale so extreme that numbers begin to lose meaning. Strangely, despite its size, it is not particularly hot. In fact, it is about 40% cooler than our Sun, glowing with a dim, deep red hue. Another red supergiant, but pushed close to the limits of what a star can become. It is so distant and so faint that you cannot see it with the naked eye. Even with its immense size, you need powerful binoculars or a telescope to detect it. Located thousands of light years away, its exact size remains uncertain. Other contenders may rival it, or even surpass it, but UY Scuti is already nearing its end. At an age of around 10 to 20 million years, it may only have a few million years left, and in that remaining time, it may not grow larger, but smaller. As it evolves, it may transform into a yellow hypergiant, an even more extreme phase, but to reach that state, it must first shed its outer layers, losing mass in violent bursts while its core grows hotter, sustaining the final stages of fusion. Hypergiants are capable of ejecting staggering amounts of material. In a single outburst, they can expel mass comparable to Jupiter. And these eruptions don't happen just once. They happen again and again. The material they release is rich with heavy elements. Oxygen, carbon, nitrogen. The very building blocks of life. These clouds can stretch for trillions of miles, forming vast regions where new stars and planets will eventually be born. In this way, even in death, these giants shape the future of the universe. Their destruction becomes creation. Their end becomes a beginning. And while UY Scuti may still have time left, there is another star even closer to this final transformation. One of the few stars ever directly imaged outside our galaxy is WOHG 64, located about 160,000 light-years away in the Large Magellanic Cloud. A red supergiant, much like UY Scuti, but already showing signs of change. In just the last decade, it has dimmed, shrouding itself in thick clouds of dust as it ejects material into space. Evidence suggests it may already be transitioning into a yellow hypergiant. But at these distances, certainty becomes difficult. Our measurements blur. Our estimates carry uncertainty. It's possible that WOHG 64 is even larger than UY Scuti, but we simply cannot say for sure. And that leads us to a final boundary, a limit written into the physics of stars themselves, the Hayashi limit, the point beyond which a star cannot expand any further without collapsing back inward. Beyond the Hayashi limit, a star cannot simply keep growing. Convection takes over, energy is transported outward more efficiently, and gravity begins to regain control. The star is forced to contract. It cannot remain that large. It cannot exist beyond that boundary. Which means that even if we one day discover a star slightly larger than UY Scuti, it won't be by much. Not unless something fundamental is missing from our understanding. Perhaps there are types of stars we have never seen, or environments we have yet to explore. And for now, we simply don't have the technology to know. But perhaps the deeper truth is this. The problem is not just distance, or limitation. It is perception. The human mind struggles to grasp anything beyond a few thousand miles. Beyond that, scale stops being intuitive. It becomes abstract. So when we speak of stars like these, hundreds of millions of miles across, we are no longer imagining. We are only translating numbers into something we hope to understand. They are cosmic monsters, but even they are not truly large. Because beyond them lie galaxies, stretching tens of thousands of light-years across. And beyond galaxies, vast distances of millions of light-years separate them. And beyond that, the cosmic web itself, spanning billions of light-years, connecting everything in a structure so immense it defies all intuition. The universe is not just big, it is vast in a way that resists understanding. And yet, we keep asking, we keep measuring, we keep searching for answers in the dark. Because maybe the goal was never to fully understand it all, but simply to keep exploring, and in that sense, living on a small planet, orbiting an average star, might be exactly where we are meant to be. Thank you for watching. If you found this exploration meaningful, consider subscribing to follow more journeys into deep space. And, as always, stay curious.